Okay, so I posted a video for you to watch demonstrating that when you pass an electric current through a discharge tube filled with pure hydrogen gas, that is H2 gas, the H2 molecules dissociate, so you get H atoms, hydrogen atoms, and the excited hydrogen atoms emit light at very discrete wavelengths. So this is the hydrogen emission spectrum. Basically, this is what happens when you have an excited hydrogen atom and the excited electrons relax back down to the ground state and they emit light at these very specific wavelengths in the visible light region of the electromagnetic spectrum. So you just see a very simple four-line emission spectrum for hydrogen. This is called the Balmer series, and you see a purple line, a blue line, a green line, and this orangey red line. You don't see a whole continuous rainbow. You just see these four lines in the Balmer series in the hydrogen emission spectrum. So the question is, what do these lines represent? What do these lines mean? Each of these lines represents transitions of an electron between discrete energy levels in the hydrogen atom. Okay, that's very important. So I'm going to write it down. So each line represents electronic transitions. So transitions of an electron between discrete means well-defined, different energy levels within that hydrogen atom. So we can kind of use this hydrogen emission spectrum as a jumping off point for the next major topic in chapter 2, which is the Bohr model of the atom. The Balmer series, the hydrogen emission spectrum, tells us that only certain energies, only these discrete delta E's, are allowed for the electrons in the hydrogen atom. Otherwise, we would see just a continuous rainbow with all the colors bleeding into each other instead of these discrete lines here, these four discrete lines in the Balmer series. So from Max Planck, the difference between the energy levels in the hydrogen atom is going to occur in multiples of h nu. So here I'm including this n as just a whole number to show that the Planck relationship can be in multiples of h nu. So we can just multiply by 1, 2, 3, etc. So again, we kind of know what these are, but delta E here is the difference between the energy levels in the hydrogen atom. Nu is the frequency of the light that's emitted when the electron relaxes back down to the ground state. And we could also relate this to wavelength, of course, because we can interconvert between wavelength and frequency using the speed of light. So we could say this is equally true, that delta E equals nhc over lambda. So what exactly does this mean? Let me draw a little picture representing the energy levels in the hydrogen atom. This sketch is going to kind of try to show the Balmer series in a semi-quantitative way. So I am going to make a little y-axis with energy represented as going from low to high as we move up. And then I'm going to make energy levels that electrons can stay in. So I'm going to make them a certain distance apart from each other. As follows, getting closer and closer together. So I'm going to call this n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, etc., etc., etc. As we go up, the difference between the energy levels shrinks, so they get closer and closer together. N equals 1, it's what is called the ground state. The ground state is the lowest energy level that an electron can be in. So I want to imagine right now that we have an electron. I'm going to make my electron in green. And let's say we excite it up to the first excited state. So when we promote an electron from a lower energy state to a higher energy state, we call that an excitation. That excited electron can then relax back down to the ground state. And when it does relax, it emits a photon. So this squiggly arrow is going to be the photon that gets emitted. And that photon is going to have an energy of h nu, where h nu is equal to the difference between the energy levels. And I can also, of course, convert it to wavelength. So in the Balmer series that we see up here, the blue line in the Balmer series comes from the n equals 5 to n equals 2 transition in the hydrogen atom. The green line comes from the n equals 4 to the n equals 2 transition. The red line comes from n equals 3 to n equals 2. So there's no way of knowing that unless I tell you. You can do some calculations to figure that out, but I'm just giving you an example of why we see those discrete lines. We see the discrete lines in the hydrogen emission spectrum because we're going from one energy level to another. And it's for emission spectra, we're going from a higher energy state to a lower energy state, emitting a photon, and you can measure the wavelength of that photon or the frequency of that photon. So you measure the wavelength of light that gets emitted, and then you can calculate the delta E. So that is the basis of spectroscopy, or basically how we figure out everything we know about atomic structure. In spectroscopy, you use a detector to measure the wavelength of the light that's emitted when the atom relaxes, when the electron relaxes back down to the lower energy state. And then from there, you can use this equation to calculate the delta E between the energy levels in your atom. So this gives rise to the Bohr model. The Bohr model of the atom is something that you probably saw way back in elementary school. It dates back to the early 20th century, 1914. And the Bohr model has a nucleus at the center of the atom and then circular orbits around that nucleus. So I'm just drawing a cartoon of it here. We could label these as n equals 1, n equals 2, n equals 3, etc., with these different n values, just like I did for the little diagram up here. Those principal quantum numbers are just kind of quantizing the energy levels. They're the one that's closest to the nucleus is always n equals 1, and then they increase in whole number values as we move out. So what are these things in the drawing? Of course, the center, as I said, is the nucleus. And then these circular orbits kind of around the center, these are called orbitals. And in the Bohr model, we have several things that kind of distinguish it. We have the electrons in circular orbit around the nucleus. We have electrons in fixed energies in a given orbital. Those energies increase as we get further away from the nucleus. And the changes in energy, delta E, come from electrons transitioning or moving from one level to another. Okay, so these last two things are pretty much true, but the circular orbit has since been shown to be not 100% valid. So we'll talk about that next when we talk about the quantum mechanical model of the atom.